Here's Physics 2 Lab 4 at Georgia Tech. The purpose of this lab is to predict the RC time constant and circuit behavior of RC circuits using conservation of energy and charge. I found that the time constant for the provided RC circuit to be 5.98 seconds. The necessary physics principles for this lab include Kirchhoff's loop rule, which states that any closed loop across a circuit will have the sum of the potential differences equal to zero. The conservation of energy is also another physics principle necessary, and it states that the sum of all the changes in the energy in the universe is equal to zero. Another equation that we will be using to help us plot our data and find the time constant is the natural log of the ratio between the current voltage and initial voltage of a discharging capacitor is equal to the negative time elapsed since the capacitor started discharging over the time constant. Here's the first circuit that we had to make for this lab, consisting of two 1.5 volt batteries, two ammeters, and two resistors in series. So at this voltage, with a resistance of 147 ohms, the current draw is 0.02 amps. Replacing one of the ammeters with a voltmeter, we find that the new current is 0 amps. This is because this empty gap where the ammeter once was acts as a almost infinite resistance resistor, because there's no way current can flow from one part of the wire to the other, and this is an ideal voltmeter which will draw no current as well. So all of the voltage drop is across this super strong resistor that has an infinite resistance, leaving the current through the rest of the circuit to be zero, and the potential difference drop across the two resistors to also be zero, as shown by the current in the ammeter. So here's a look at the potential difference versus the circuit location. We start at 0 before the batteries, and once we're past the batteries, we're at 3 volts, from 1.5 from each of the batteries. It's constant until we get to the first resistor, then it decreases, and then it's constant until we get to the next resistor, and it decreases again. So using the loop rule, we know that after passing through the two resistors, the change in voltage must equal the EMF from the battery. So once we're past the 100 ohm resistor, there are 0 volts until we return to the battery to be recharged. Why doesn't adding a voltmeter change the ammeter readings? This is because the voltmeter has a very high resistance. Ideally, it will draw 0 current. So if you have it in parallel with something else, none of the current will go the route of the voltmeter because of the incredibly high resistance. So the current just stays the same. If you have something in parallel with an ammeter, ammeters are meant to be in series and have ideally 0 resistance. So if something's in parallel with it, all of the current will go the path with the ammeter, leaving the potential difference to be used up in another resistor. So overall, your amount of resistors have gone down, and the overall current must go up to compensate for that. Calculating the potential difference values and resistance values of the 47 and 100 ohm resistor, I got 48 and 102 ohms respectively. Now, I know this does not match up with their designated values from the simulation. However, this is due to rounding error, as the simulation only gives you 2 to 3 decimal places to work with, so there's just a bit of discrepancy due to rounding. Here's a look at an RC circuit, initially uncharged and then in its charged state. You can see how initially the bulb was bright and there's no charge. Now the bulb is off and there is charge built up on the capacitor. So discharging, we start with the capacitor in its charged state. The bulb is off, no current flow. Once we remove the battery, all of the charge dissipates, discharges out of the capacitor, and the bulb lights up and slowly gets dimmer until it turns off again. The procedure for this lab was to charge the capacitor, then remove the battery, and record the initial voltage reading across the capacitor, which should be the same as the voltage supplied by the batteries. So once the voltmeter is attached across the capacitor, you will play the simulation and let it discharge, and record the voltage across the capacitor every 2 seconds for 20 seconds. Once you have your data of initial voltage and voltage versus time, you can make a natural log of current voltage over initial voltage versus time, and the slope of that graph will be -1 over the time constant, which was seen earlier in the fundamental physics principles section. So I got my RC value to be 5.98 seconds, while theoretically it should be 6 seconds. It's not too far off, and this discrepancy is probably rooted in the rounding errors provided by the simulation. If we use an actual ammeter instead of a simulated one, it would have some measurable amount of resistance, so the current and potential difference readings would be lower. And if a real battery was used to charge a capacitor with no resistor, it would charge almost instantaneously, but because of a little bit of inherent resistance, it would still take some fractional amount of time to charge.